say that probably over the first term there should be some basis vector. If you look at that one, second term you have basis vector, and like first term there should be probably.
You're right. You're right. Thank you for catching that. So, essentially, what he's saying is, what we derived was that this is, by the product rule, going to be equal to the derivative of this, which is equal to this. Oh, wait, sorry. This times the basis vector plus the derivative in the basis vector times the original. So, yeah, okay. So that is very good. Thank you for catching me on that. Awful symbols. So essentially, what are we trying to cover here today? What does the Riemann curvature tensor or the Christoffel symbol even mean? Well, imagine we're in a room, right? So let's say we have a room right over here. So then, what I'm going to do is I'm going to introduce a distribution. So, for example, one distribution could be temperature. At every point in the room, there's some amount of temperature. In this point, maybe it's 10 degrees Celsius. At this point, maybe it's 15 degrees Celsius. And of course, there's no point where there is no temperature value assigned. It's not like I can walk right over there and say, I can't measure the temperature right here. Every single point in this room has, let's probably use white so it's more visible. Every single point in this room has a temperature assigned to it. So this is what we call a scalar field. So for example, a symbol for a temperature scalar field would be T. So now, here's the definition of a covector. Let's say I'm in this room and I walk all the way across it. I record the temperature difference. Maybe, for example, this one is 5 degrees Celsius. This one is 6 degrees Celsius, a little bit hotter. So, of course, the difference is 1 degree Celsius. And then divide that by the length over here and multiply it by the direction of the vector. So then what we're going to do is, instead of doing that, we're going to make it a little bit shorter. We're instead going to be walking from this side of the room to maybe around here. And we measure that it's, say, 5.7 degrees Celsius. And then we get a little bit closer. We say we measure, for example, 5.2 degrees Celsius. And we keep continuing until at some point we just have a differential ds pointing in this direction, and we're moving to this very small point that's right next to our original point. And then all we do is we take this change in temperature, we divide it by the magnitude of this, and then we multiply it by the direction of this. Now, what notion does this kind of seem similar to? Well, the derivative. I take a regular single variable function. All of you obviously know that if we have 2 points, we draw the secant line, then we bring one of these points a little bit closer and draw the secant line again, and keep going on and on. Eventually, the slope of the secant line will approach the true value of the derivative. The same thing goes here. As the distance becomes closer and closer, no matter what the direction is, then we approach the true derivative at this point. And this is what we call a covector. But, of course, it's not limited to scalar fields. So, one thing you may notice here is that this is very similar to a notion that you've already learned if you've taken multivariable calculus, which I'm pretty sure most of you have. So, of course, let's say we have this room. Let's pretend it's a two-dimensional room so I can visualize it here. Let's say we have this room. Since every single point in the room has a temperature assigned to it, that means we can express it not just as a distribution, but as a surface, where the z value over this room is going to be the temperature. Like over here, it might be really high, and over here, it might be really low. And we can draw the total temperature as a sort of surface, maybe one that looks like this. So then what I just did was I took a point here, and I essentially kind of took the derivative in a certain direction. Now, of course, took the derivative in a certain direction kind of gives you a hint about what it is, but of course, this is just going to be the directional derivative at that specific point in a specific direction. But, of course, a covector isn't just a directional derivative multiplied by a unit vector. Covector is so much more than that, actually, because it doesn't just work with scalar fields. It's kind of a generalization of regular directional derivatives, not just scalar fields, but also vector fields and tensor fields in general. So, now, this is what we call the covariant derivative. Now, for a scalar field, this is very simple. All of you know how to take the derivative of a surface, like this, right? What do we call the derivatives of the surface in all of the basis directions? Everyone has an idea, right? What are they called? Does anyone want to raise their hand? Or all right. So these are what we call partial derivatives. They're just the derivatives in all the basis directions. I, J, and K. So, in the same way, we're taking partial derivatives of these directions. J and K, well, of course, we can also take the derivative of it along K, but I'm not going to do that right now. What we can do is, of course, express that as a vector. Partial f x, partial f partial y for a two-variable function, and if it's a three-variable function, you can also introduce f partial z. Now, the point of general relativity is to generalize this to anything we can. So no matter how many components we have, we want to make sure this works. So instead of writing it this way, what I do is write it like this. Partial f, partial x mu. How does this work? Well, essentially, what it's doing is, mu is kind of a stand-in for all the numbers. Mu could be 1, mu could be 2, or it could be anything greater than that. Of course, traditionally, 2 is assigned to y, and 3 is assigned to z. But of course, the good thing about using numbers instead of letters is that you can go beyond that to as many dimensions as you like. So, or even 100. So that's what's so neat about mu. And how can we write this as a vector? Well, the thing is, this is not like a quantity in itself. Mu is not a number. Instead, what we're writing like a summation, where we have the vector so that the first component is where mu is 1, the second component is where mu is 2, and the third component is where mu is 3. Now, of course, this is actually the covariant derivative in a basis direction for a scalar field. Pretty simple. So, let me just erase everything really quickly. So now, we know that the covariant derivative, that whole notion of walking in a room with a certain temperature, the covariant derivative in some basis direction of our function is just equal to the partial derivative of that function over the basis direction. Now, I've got a very special question for you, actually. This is, of course, true for scalar fields. I would never lie to you. But what happens if suddenly we move to vector fields? What happens if we try to generalize this? Well, what's the simplest way to generalize this kind of thing? We get that this is going to be an output of a vector instead. So let's write nu over there. And of course, since it's a vector instead of a scalar, I'm probably not going to use f, but instead v. Actually, no, v looks too similar. What can I use? Probably capital F. So, the natural assumption would be to write this. But is this correct? Does anyone have any ideas? If this is correct, is this correct? Anyone? Yes or no? Yeah. So, it must be pretty hard to see. No, the thickness is very low. I could barely read it from where you were sitting, so can't imagine people in the back could see it. So what I'm going to do is make it a little bit bigger. So we know this is valid. But now what we're trying to do is to a vector field. So we're adding this component to signify that instead of a scalar. This is going to be equal to this. Does anybody have any ideas? Okay, I'm going to take that as a no. So, of course, this seems like a plausible assumption because all we're doing is we were able to take this scalar and work it out. But so we should be able to take this vector and work it out the same way. But the answer is no. Let me make sure I don't break anything again. This is not the covariant derivative of the vector field. Why? Well, let's look at it. Let's say we have a very specific vector field. And this one is going to be in polar coordinates, r comma theta. So, say we have the specific vector field so that the r component is always 0 and the theta component is always 1. Now, I would probably take a wild guess and say that looks something like this. With it kind of curling around and getting bigger as you go out. And of course, this is correct. But that's not what our notion says. So of course, this is wrong. So now, let's test it out over here. So, of course, what is this going to be equal to? Well, let's look at what each of the components are going to be. So we're going to have kind of a vector of vectors in a sense. So the first component of our gradient over here, the first component of our partial derivative is going to be when mu and nu are both 1, i.e. both of them are the r component. This is going to be our first component. So now, of course, what is fr? 0. What is xr? Well, that doesn't actually matter for our purposes because this is always going to go to 0. And of course, the second one follows the same logic. It's going to be r on the top and then theta on the bottom. But since fr is always 0, it doesn't matter. And the second vector is going to follow the same exact way because this is instead going to be partial f theta over partial x mu. And of course, what is that? Well, f theta is a constant function, 1. It's not like it changes, right? So the partial derivative, or the derivative in general, for anything that doesn't change is, of course, 0. And that holds for both of them. So wait, this is telling us that the change in the entire vector field should be 0, i.e. it should be looking something like this. But I don't know about you, something is telling me this field is changing over time. If I walk from here to here, the vectors have definitely changed. Not just in magnitude, not just in direction, but also in magnitude. So something is clearly very wrong with our assumption. But what is it? So erase this. So what's wrong with our assumption is actually something very, very simple. It doesn't account for the change in basis vectors. Because, of course, Cartesian coordinates, this perfectly works. But that's only because the basis vectors are always 1, 0, 0, 0, 1, 0, 0, 0, 1. They never change. But the problem with these coordinates is that they do change. So, what we're going to have to do is account for that. So, we're going to write a special notation for basis vectors now. So, in Cartesian coordinates, you all know the basis vectors is I, j, and in 3 dimensions, k. But we're going to stick with I and j for now. So then, what do we denote them as? Well, this is I, so we're going to write it as E1. And this is j, so we're going to write it as E2. Oh, wait, no. These should be subscripts. Now, you might be asking, why am I writing some components as superscripts and some as subscripts? Well, the difference is the ones where we write superscripts are regular vectors that we all know and love. But the ones where I write subscripts are covectors, the ones that we just discussed. So we have E1 and E2 right over here. And of course, if we were to add K, E3. And once again, the advantage with numbers is, unlike letters, we never run out of them. And we can also generalize them. Because in the same way, R and theta can be written as E prime 1, E prime 2. Of course, that is if you consider polar coordinates to be E prime. I'm just writing it this way so we don't get confused. But in general, if we're just dealing with one coordinate system, we call the basis vectors E sub k. Great. So, now we know how to denote basis vectors as well. So how do we denote the change in bases? First, we're going to want to know how to write vectors in the first place, which uses Einstein's summation notation. So basically, what I'm saying over there is, over here, we said we can essentially write a vector, like for example, we can essentially write a vector, like for example, 1, 2, 3, which is a normal vector, so we're going to use superscript, with this one component, the rank 1 tensor. So this one component is going to be expressed very usefully. What we're going to do is, we're going to write 1, 2, 3 over here, and in Cartesian coordinates, how do we access every single component over here? Well, we get that essentially what we're doing is we're taking the component, which this is a regular vector, so we write a superscript, and then we multiply that by the basis vector. Of course, what this is, as you know, 1i plus 2j plus 3k. No? So in the same way, we already know I is going to be equal to E1, j is going to be equal to E2, and k is going to be equal to E3. So what that does is it allows us to write the first component, v to the power v1 times the first basis vector, e sub 1, plus the second component, v2, times the second basis vector, e sub 2, plus the third component, v3, times the basis vector e sub 3. And what we do is we write this in general, not just for vectors that have 3 components, but for vectors that have 4, 5, and so on components, by simply writing this as sigma over mu, so mu equals 1 to however many components it has, of v mu e mu. Wonderful. So that's how we can express a basic vector. And this doesn't just follow for Cartesian coordinates, for any coordinates in general. So now, what can we do in order to find the covariant derivative of a vector, like we were trying to figure out in the beginning? So, the covariant derivative of this vector function is equal to what? Well, as we guessed with the scalar, it's going to be partial f, partial x mu, but there's going to be a second thing added to it in order to account for the change in our basis. So that's going to be, via the product rule, what we're going to do, we're going to write this as f1 e1 plus f2 e2 plus and so on and so forth. So, right in this case, it's going to be v equals 1 to how we have, say, n of fn en. Now, all we have to do is use the rule. So, essentially, all that means is we have, this is going to be the derivative of, so divided by x mu, like we guessed, and then plus an additional factor, which is going to be the change in the basis vector, which we write as dE, and what I'm going to do is go to use, let's see, so the change in the basis vector that we're using times the original, which is going to be this. So this is how we write the covariant derivative. Now, we're going to get to the Christoffel symbols. So what are the Christoffel symbols? Let's answer the question we had at the beginning. Why are they useful in general relativity? Well, here's the thing. Let's just see this. Let's say we have, for example, just a ball falling through flat space. Let's say it's a massless ball, so it doesn't affect space-time. So let's say we just have a flat space-time right over here. So, in this space-time, it's going to fall from a point A to B. There's only a single path it can take. It's not going to go like this. It's going to go straight from A all the way down to B. That's the shortest path between 2 points. And if we are instead on a curved space-time, like a sphere, and we want to get from some point A to some point B, oh, let's use yellow. What do we use? On the surface of the sphere, we could just whoop-de-doop. That's not the shortest path. The shortest path is not a straight line either. It's actually what we call a great circle. And for example, the equator is a great circle. Just a line that goes all the way around the circle. The sphere, sorry. So, this is what we call the geodesic. The shortest path between 2 points on a surface. And the geodesic heavily relies on our Christoffel symbols. So that's our motivation for doing this. Now, what are the Christoffel symbols anyway? Well, Christoffel symbols are just functions of the metric tensor. But then we're probably going to say that doesn't mean anything. What is the metric tensor? We've never defined that. Well, that's a great question. The metric tensor in itself is an interesting concept. Let's say I want to know the curvature of a space. What I can do is I can first take one point, and all I'm going to do is I'm going to draw a closed loop that's differentiable everywhere. It goes all the way back to this point. So over here, what we get is this. Now I go to draw the tangent vector. So we find the tangent vector everywhere. And here what we're doing is we're assuming we're on a flat space-time. So we have this, goes around again and again, and then eventually it returns back to its original position. But now let's say we're on a curved sphere, and we draw the same kind of thing. Some sort of loop that's allegedly not differentiable everywhere. And now what I'm going to do is draw the tangent vectors again. But clearly there's a difference here that we didn't witness over here. Yeah, there's a 0-degree difference. So what gives? Well, essentially what I'm trying to say here is to talk about the curvature of any space, what we have to do is find the length of every single vector in that space. So essentially, we have a sheet of paper, then I deform it a little bit. What we're going to try to do is find the length of every vector in that new deformed space and compare it to the original. So like, if I have a piece of paper here that I bulge in the center a little bit, I don't know how to draw, but essentially, if I bulge this paper in the center a little bit, then the directions of the vectors over here in the new curvilinear coordinates, the magnitudes of these are going to be slightly affected compared to if I just leave the paper flat. So, what I want to do is to tell me the curvature of the space, I want to get the magnitude of every vector there. And how do we get the magnitude of a vector? Well, that's very easy. All we need to do is take the vector itself, then dot product it with the same vector. And that'll get you the magnitude squared, which of course then you can square root to get your own thing. But that's not what we're really concerned about. What we are concerned about is actually finding these magnitudes. Because if we square it, there's not really that much of a difference. It's just kind of a proportionality constant. It's still increasing or decreasing at some point. So we have v mu dot v nu is going to be equal to, well, v dot v is going to be equal to, as we said before, we can express a vector like this, v mu e mu. And of course, what we do in Einstein summation notation is we kind of hide these sigmas. But we know that we're summing over something. There's one contravariant index, or one regular index, and one covariant index. So one subscript and one superscript means we're summing over that index. So instead, this is just going to be v mu e mu dot mu e nu. And you might be asking, wait, why are you using two different indices over here? In Cartesian coordinates, so that taking the dot product between two vectors multiplying component 1 by component 1 of the other vector, plus multiplying component 2 by component 2 of the other vector. 1 times 3 plus 2 times 4 is equal to 9. But there's a very hidden caveat that sticks out over here. Cartesian coordinates, this works. This is perfectly fine. Why? Well, this is only because the Cartesian axes are perfectly perpendicular. But as soon as you deform them from being perpendicular, then this no longer works. So why? Well, think about it this way. What is the dot product of two perpendicular vectors? Everyone knows that, right? What's the dot product of two perpendicular vectors? Louder? Okay, good. So, since we have that these two basis vectors are perpendicular, and we're basically dot producting these two vectors with proportionality constants, then that means, since we take the dot product of one with the other, unless they're the exact same vector, we always get 0. So, here's what I'm essentially saying. We're taking the dot product of the vectors 1, 2, 3, and 4, 5, 6. So everybody can work this out quickly, right? What's the dot product of these two vectors? What's the dot product of these two vectors? Anyone? Okay, good, 32. So, the way you all do it was 4 and 3 times 6 is 18. And of course, you guys are very quick summers, so this is going to be 32. So now, this actually has a caveat. Where I dot 4i. And of course, you all know what I dot I is. In Cartesian coordinates, dotting a basis by another basis always gives 1. 4. 1. Okay, you guys are doing good. When I dot k, that's going to be. And crap. Okay. And we keep forward. So all we got is 1i dot 4i, which, as you guys said, is 4 times 1 or 4. So then, let's move to the next one. We multiply 2j by 4i. And what is that? We multiply 2j by 5j. What's that? Okay. So, Cartesian coordinates. And as a bonus, polar coordinates, since r is always perpendicular to theta. But this doesn't work. Basis vectors aren't perpendicular, which is why we're generalizing it like this. So then, what we get is something very special. All we get is, this is v mu, v nu, and this, of course, can just be a proportionality constant. What we really care about is the product between e mu and e nu. And that is what we call the metric tensor. So this is just telling us how long is every vector when compared. And it's defined as mu nu e mu dot e nu. So now let's get very cheeky term. Because of course we already know how to calculate this. This is just a gradient. But how do we calculate this? Well, that E mu, as we see, let's use the letter E mu. And this is partial derivative over some direction. Side, starting with this new index, lambda. Okay, let's see. Now, using our definition, oh wait, this would be lambda. Sorry, oops. By now, what we get is that this, of course, we already know the definition of this. This is G, the metric tensor, lambda nu. And right here, we have also emu dot e nu. Emu dot e nu. This is a tongue twister. So eventually, by the product rule, what we get is that this is equal to this. Actually, I need some more space. Equal to this plus so we can all tell this is just the basis vector in our certain direction. Is this equation, which I know. Wait, how many indices are? Oh crap. Okay, 1 second. Sorry, that's. We're dotting over some dummy index, alpha. So this is just. So this is going to be partial nu e mu dot e alpha plus partial nu e alpha e mu. And this is going to be equal to the Christoffel symbol times the metric sub lambda alpha. Let me just rewrite that here a little bit. This is, of course, the metric alpha, and we add that to this. And this is equal to lambda alpha. And of course, all we're going to do is, I'm going to keep it short for the sake of brevity, but all we're going to do is, we're essentially going to do an index swap. So what we have here is, we just randomly introduced this new index. This is just a dummy index, doesn't matter what its name is. Alpha. So instead, what we're going to do now is, the limit of these, which are the only ones actually specified, essentially cycle through them. Because their names in themselves don't matter, just their positions do. So essentially, mu is going to become nu is going to become lambda is going to become mu. And then we're going to repeat that cycle twice in a row. So of course, the two other ones we get are going to be, this gets changed to lambda, g mu gets changed to mu alpha, plus partial mu gets changed to lambda, e alpha, dot, which gets changed to we mu becomes lambda, becomes mu. And lambda becomes mu alpha. And of course, you might realize this is the exact same as this term right over here. And then we cycle through it one last time to get all three variations. So we do this whole cyclical transition again. Lambda becomes mu becomes lambda becomes mu, alpha, mu becomes lambda, mu becomes mu becomes lambda becomes mu, times g, mu cycles around 2, which of course this is the same as this. And through a system of equations, what you can do is, I'm not going to do algebra, but all of the steps you have to execute. You have to use a property. The symbol is symmetric, which all arises from the fact that the Christoffel symbol is a function of the metric, and the metric itself is symmetric, because of course it's metric. So we utilize that it's symmetric on its lower two indices. Alpha is equal to mu alpha lambda. Then, secondly, all we have to do is solve for the specific mu lambda. And turns out this is going to be half times g alpha beta. And what we're going to do is, this is, wait, no, is this alpha beta? No, pretty sure it's lambda alpha. This is, you might be asking, why are they on top? This is just the inverse of the regular. So g lambda alpha to the minus 1, of course, it's a matrix, so you could do that, equal to this. So I'm going to try for the I think I should rewrite this somewhere else, because this is getting a little bit too okay, what the heck? The erasure has become lodged in between, so let's just remove that. Okay, there we go. So, this must be grading systems. I have no idea what this says. Alright. Just go into a little bit. All right. Oh. So I'm going to rewrite this over here. This Christoffel symbol is going to be equal to half g lambda alpha times the partial derivative over mu g lambda plus the partial derivative over mu this should be alpha, sorry. Lambda plus partial alpha g mu. Great. So, oh wait, this should be a minus. Oh my goodness. That is our equation for the Christoffel symbol. Great. And now finally, we're going to get to know, we're not going to cover the geodesic equation in this one, but finally, we're going to derive very quickly the Riemann curvature tensor. So what is Riemann curvature tensor? Well, essentially, we have a notion that we call parallel transform. So essentially, we all remember that the shortest path, essentially, what the heck is that? The shortest path in a flat spacetime is going to be a straight line. So we draw a path from here to here to here. And now, all we're going to do is we're going to essentially parallel transport a vector. But this vector is going to look the exact same everywhere we go. But let's say we try to do the same exact thing on a curved space, like a sphere, for example. And we draw our path right here, made from the geodesic. So these are partial versions of three great circles. And so, let's see, this should be right over here and over here. So then, what's this going to be? Well, we parallel transport a vector right over here. And it seems okay, but here we actually have to make a sort of transition because, okay, well, how can I explain it in a better fashion? Oh, okay, here it is. What we're essentially doing is, instead of just a tangent vector, you guys all know what a tangent plane is. Tangent plane to a surface just touches it at one single point, describing essentially the space of the partial derivatives, the two partial derivatives. So what we're doing here, we're drawing tangent planes at every point. So for flat space-time, the tangent planes don't change at all. The tangent plane to a flat plane is what? What is it going to be? Well, it's just going to be another plane. I mean, that's the only thing that can be tangent to it. And, I mean, if you want to actually show this, of course, a tangent plane is just a plane formed by its two partial derivatives. So partial x, partial f, partial x mu plus and partial f, partial x. So partial x1, partial x2, and of course partial x3. But the problem is the partial derivatives in all three directions, since this is just a flat plane, are going to be 0, 0, and 0. So that means the two vectors that form this are going to just be the 0 vectors, which causes it to be a flat plane. Great. So then, that means that if a path and then we take the flat plane at every single point on this path, and we draw the perpendicular vector. Since the flat plane never changes, the perpendicular vector never does either. It's always just sticking directly outward of the page. But now let's try that on a curved surface. if we draw some paths over the geodesics, like this, and back over here, we draw some paths just like that, then what I'm going to do is actually change color for a second. Great. So, of course, the tangent plane right over here is going to be kind of flat. The tangent plane over here is going to be kind of wacky. And the tangent over here is going to be in that direction. So, great. Now let's draw the vectors. It's going to be like this, like this, like this, like this, like this, like this, like this. And I'm trying to draw them so that they're very clearly sticking out of the page. But, we found a very big problem. The tangent plane, when we go over here, which I'm going to draw like this with blue color. Okay, let's bold in our lines a little bit. So the original tangent plane, as you can see, looks like this. But the tangent plane, when we go all the way around, we loop, is going to be looking like this. There's a rotation of some degree. So the parallel transport has failed. Instead of it being the same, instead of it being the same when we start at a point and then go all the way back, it's changed. And that is the property of a curved system. Now, what does the Riemann curvature tensor do? It measures that change. It measures this little angle in between these two. So the Riemann curvature tensor is just a tensor that measures the change in a vector as you parallel transport it, and by extension, the curvature of a space. So now, how do we derive it in actuality? Well, the trick is that we use what we call the commutator. Now, of course, you can do the thing I just did, where we're taking the difference between not doing anything and going around the loop once. But a similar way to do things is checking what happens when you go around the loop clockwise versus when you go around it counterclockwise. So we're going to do that. So if we're going around the loop clockwise, that means we're applying the first transformation and then the second. And we're doing that to some random parallel transport vector, v lambda. And then we're subtracting the difference between that and the other one, which is going to be going in counterclockwise, means you're just reversing the order of what transformations you're applying. Now, of course, in the examples we showed, we actually applied 3 transformations, A to B, B to C, and C to A. But this derivation works with only 2, so we're just going to go with that for simplicity. And v lambda. Now, of course, factoring out v lambda, subtracting these yellow parts gives us what we call the commutator. So first, let's actually take this. Now, this is just the covariant derivative over mu of whatever's inside. So let's see. I don't know if we have much time left, but I'm going to attempt to cover this. So taking the derivative of what's inside, we get this original. And then we add that, of course, to the change in our basis vector, which is going to be over here. Let's see, what do we use for it? Oh, right, just a dummy index. Let's say alpha. And then we multiply that by the regular vector. Okay, great. And, of course, this is just going to be the same exact thing. And this is going to be the same exact thing, but with mu and nu swapped. So the paper that I saw uses this notation, so I'm just going to use that. So essentially, we have this minus the same thing with mu and nu rotated in indices. So what happens now? Well, we just take the covariant derivative of this once over again. And eventually, doing all the algebra, which I'm just going to compress right now, gives us the Riemann curvature tensor, which is a function of, wait, I should be able to remember this, which is a function of the Christoffel symbols. So it gives us four dummy indices, three being contravariant, and let's see, am I doing everything correctly? Yeah, three being contravariant and one being covariant, and we're just multiplying that by, three being covariant and one being contravariant, and we're multiplying that by the original vector. So then, wait a second, have I done everything correctly? This should be swapped. Wait, no. Let me just think. Yeah, okay, this should be correct. So, this is how we write the Riemann tensor. And of course, when we're writing the field equation, we can track this into the Ricci tensor. Because in most cases, we can actually say nu and alpha are the same exact thing, which allows us to drop these two dummy indices and rewrite this as r mu lambda. So that's essentially how we go all the way from learning about covectors and deriving the Christoffel symbols to deriving the Riemann tensor and, by extension, the Ricci curvature tensor. So that's it. I hope that you all have at least learned the general concept, and thank you everybody for attending today's lecture.
I just wanted to say that probably over the first term there should be some basis vector. If you look at that one, the second term you have basis vector, and like first term there should be top two.
You're right. Thank you for catching that. So, essentially, what he's saying is, what we derived was that this is, by the product rule, going to be equal to the derivative of this, which is equal to this. Oh, wait, sorry. This times the basis vector plus the derivative in the basis vector times the original. So, yeah, okay. So that is very good. Thank you for catching me on that. There's a similar mistake, actually. So I'm going to rewrite this whole thing as partial v lambda partial x nu plus, as you said, the basis vector partial x nu. That's very good. Thank you for catching me on that. And of course, I think with this, we can actually the derivation quite smoothly, but due to time constraints, I'm not able to write out the full thing. Thank you.
Okay,
Right.
So,
Okay, that's great. I actually didn't use a book, but rather several papers on how to actually teach general relativity. So the one that I source from most is a paper from Sonoma University. I'm gonna see if I can find it for you, because I don't remember the exact name, but it should be the General Relativity Primer, and it's a 31-page document on essentially how to teach general relativity. Thank you.
खोलो खोलो दरवाजे पर्दे करो किनारे खूंटे से बंदी है हवा मिल के छुड़ाओ सारे जाओ पतंग लेके अपने ही रंग लेके आसमां का शामे आना आज हमें है सजाना। क्यों इस कदर हैरान तू मौसम का है मेहमान तू। ओ दुनिया सजी तेरे लिए खुद को जरा पहचान तू। तू धूप है झम से बिखर, तू है नदी ओ बेखबर। बह चल कहीं उड़ चल कहीं दिल खुश जहां, तेरी तो मंजिल है वही। क्यों इस कदर हैरान तू मौसम का है मेहमान तू। खुल गया आसमां का रास्ता देखो खुल गया। मिल गया खो गया था जो से तारा मिल गया। मिल गया रोशन हुई सारी जमीन, जगमग हुआ सारा जहां। हो उड़ने को तू आजाद है, बंधन को ही अब है कहाँ।